Welcome everyone. Thanks for watching my video and thanks to the organizers for the opportunity to give this talk, which is about inflation beyond perturbation theory. So, um, this talk is based on two papers with Paolo Criminelli, Giovanni Tambalo, and Vicharit Yingcharenrat. So I usually like to say that primordial cosmology is like a detective story when you use observational data to constrain the statistical properties of primordial fluctuations left over from inflation, and when compare this to theoretical data that maps the physics of inflation to these statistical properties. But usually we do that in a very precise manner. We look at small fluctuations on top of our preferred background, and we compute a few endpoint correlation functions where we think that most of information lies, typically the 2-point function, the power spectrum, the 3-point function, the bispectrum, etc. But we know that this fails for rare large fluctuations. This is okay to compute correlation functions, but not more. And that's well known because when you teach non-quantitative to students, you really stress that FNL is not the true expansion parameter. This is FNL times zeta. We usually think about it as FNL times square root of p zeta, the typical size of fluctuations, because we think of typical fluctuations. But truly, the expansion parameter depends on the size of the fluctuation, and when it becomes too large, we need a non-perturbative method. So there are many motivations for our study. First, it's simply fun to be able to compute the wave function of the universe, as I will show you, for the interest of it. And then there can be surprise also, of course, in the data and details, because that's a subject that hasn't been touched a lot. And as I will show you, there are also unexpected regime that we have discovered. So here is the outline of the talk. First, I want to show you how to go beyond perturbation theory, and then discuss two subjects related to the two papers about resonant inflation and a new regime. So how to go beyond perturbation theory? The main idea is simple. I recall that inflationary fluctuations are of quantum origin. We usually put h bar to 1 in our computations, but truly we use the uncertainty relation. Computation between q and conjugate momentum is I h bar. As a result, the typical size of fluctuation is set by the square root of the power spectrum, fine, but we forget the fact that it's proportional to square root of h bar. So when one look at a rare fluctuation with zeta much larger than that typical values, okay, you can think about it as large zeta, but at fixed zeta, you can also see it as taking the semi-classical limit, h bar goes to 0. So zeta typical small. So one can use that in the framework of the wave function. So let me recall you what the wave function is. It's, strictly speaking, a wave functional. It takes as an input the profile in space of the primordial curvature perturbation zeta, here called zeta bar, because that's a fixed target we are aiming at. And this object gives you the transition amplitude to go from the Bunch-Davies vacuum in the far past to that given configuration with weight given by the action over h bar that I put again to recall this fact. So usually this is computed perturbatively, but we can very well study non-perturbatively in the large zeta bar regime. Then this is dominated by the solution to the classical nonlinear equation of motion with boundary conditions, Bunch-Davies, and the final one we are aiming at. And this has been put forward in this paper, where they show that this corresponds to resumming all the tree-level diagrams, all the tree-level nonlinearities with negligible loop effects. So a few remarks. It's very different from other approaches like stochastic inflation because it takes into account the quantum physics inside the Hubble radius, which is trivialized in stochastic inflation, and here, which is central to the whole subject. Second, you can really ask crazy things like, what is the probability of having the Stephen Hawking signature in the CMB map? That's a full morphological information that goes beyond, let's say, the 1-point or the 2-point PDF, and we can have answer to such questions. Okay, but then practically we need the action, and usually we don't know the action for the perturbations fully nonlinearly. That's what we did in our first paper. Here is actually the full non-perturbative expression of the action valid in all models of canonical single field inflation. So single field with potential. It's a reformulation of the action and of the EFT of inflation, which is valid in the decoupling limit, so small epsilon, and therefore all you can consider constant h. And that makes manifest the super-Hubble conservation of the Goldstone boson pi. So basically all the non-trivial nonlinear information is encoded in that function h dot as a function of t. And once you know it, it encodes all the nonlinearities of that model. So in the following, I will use the symbol zeta bar for the final configuration related to pi bar through that simple rescaling because of the decoupling limit. And I will also use the same notation, zeta simply linearly related to pi. All right, so we have the receipt, we have the action, and we have the method. Now let's apply it to a specific example, and which shows resonant inflation, which is a super well-known setup. It corresponds to single field inflation with an almost flat potential of slow roll type, plus superimposed oscillation with a typical potential cos phi over f of the type of, if you want, axion inflation. In our framework, in the EFT of inflation, that corresponds to h dot being roughly constant, plus a small correction, which is a cosine of omega t. There are two parameters that are important, the frequency omega, and I will use the frequency in Hubble units. We will call it alpha, and alpha will be large, typically quite larger than 1. And there is also the amplitude of these small features, which precisely we will take to be small. And so this is a well-known setup that has been studied. There is a resonance between the two types of oscillations, the background oscillations of in exponential I omega t, and the one of the quantum modes in exponential I k eta, where eta is conformal time. And this leads to resonance inside the horizon and enhanced non-causality with peculiar shapes. So that's the setup. Now, what did we do? Very important thing, we worked at first order in the amplitude of the feature, small b, first order in b. With that, you will not be surprised that we can evaluate the action on the solution with no feature. It's very similar to the fact that, for example, for experts of non-causality, that we can compute when we compute the third order action, we only need the labs and the shift at first order. That's really the same reason. So that really makes our life very simple. You take your profile you are aiming at, zeta bar in real space, you Fourier transform it, you obtain zeta bar of k, and here it is. You know the free solution corresponding to that profile at late times, and that has the correct Bunch-Davies initial conditions. Here, tau corresponds to weak rotated conformal time. Once you have that, you just have to plug it into the action, and you will find the wave function. There will be a Gaussian part. Okay, fair enough. And there will be the first correction, delta S Euclidean at order 1, that gives you the correction at first order. And I don't give the explicit formula because it would be a bit crowded, but the point is that the problem is solved at that stage. You just have to perform a space-time integral of explicitly known functions, zeta bar, and the cosine, if you want, in the action. And you can numerically integrate it, that's what we did, or in some regime, in particular the regime of large frequency, alpha large, go to saddle point analytical reasonings. All right, let me stress now also a few facts. As I stressed, this corresponds to resumming all three-level diagrams at order B. Let me say B for simplicity. You can look at the scaling of these wave function coefficient diagrams and easily convince yourself that when alpha squared times zeta becomes of order 1, then you really have to resum everything and perturbation theory crashes. That's one thing. The second is that in these specific examples, each diagram has a counterpart at the loop level at first order in B, but they are actually suppressed by this parameter alpha squared times the power spectrum. So actually, in this regime, it's perfectly fine to neglect loops, not only in the tail, but also for typical fluctuations. And as a result, we have the wave function everywhere. So that's quite nice. Now in practice, what did we do? We chose a simple spherically symmetric profile of that type, and we simply varied its amplitude so that we can have a simple plot in terms of one number, if you want, and not a full functional. We fixed the functional dependence and just vary the amplitude. So in the plot I will show you, there will be one-dimensional, and zeta bar will go from minus infinity to infinity, and negative corresponds to trough, minima of the curvature perturbation, and positive zeta bar correspond to peaks. And the plot I will show you again correspond to this correction in the exponent of the PDF. What did we find? So here again, zeta bar positive and negative in two plots for simplicity. You see for different values of alpha that the smaller, the larger the alpha, let's say from 6 to 7 to 8 and 9, the smaller value of zeta bar, something starts to become crazy. And indeed, there is an exponential growth precisely where perturbation theory tells you that something breaks down. But the way these things break down is very different on the right and on the left. See the different scales. There is a huge asymmetry that is very hard to guess, actually impossible to guess in perturbation theory, in the probability of having peaks or troughs. And concentrating on the right for simplicity, once we arrive in this regime of large values of zeta bar, actually the growth saturates, as you can expect, and you get oscillation on the tail. And we even have an analytical understanding of that in the saddle point analysis that I've mentioned for large frequency, where the oscillation is due to that first factor, exponential I alpha zeta, and the very large amplitude on the right compared to the left is due to that factor that is absent for local minima. And we actually have an understanding of that in a toy model in quantum mechanics. Okay, so far so good. Now let me motivate the second topic. I've said that we need to resum, if you want, the full wave function coefficients to really get the full PDF when alpha squared zeta bar is larger than 1. But what about if we need that actually for typical fluctuations? That would be a weird regime, and that's the one we considered. A priori, if you look at what it corresponds to in terms of the parameter of the model, that corresponds to the frequency omega greater than 4 pi f. Usually, we say that 4 pi f is the cutoff of the series with the cosine phi over f. But that's actually not true, as pointed out in a paper by Hook and Ratazzi. It cannot be true because when the amplitude of the feature disappears, when b goes to 0, the theory becomes free, and so the cutoff should go to infinity. And indeed, there are logarithmic corrections that increase the cutoff beyond 4 pi f. And our point was, well, what are the observational implications in this regime? So here is straight the answer. This will be a new regime with a lot of information in a large n endpoint functions. So where the information will not only be encoded in the 2-point and 3-point function, but in a handful of, let's say, 3 to 9 endpoint functions. So for this, we need to identify what is the precise unitary cutoff of the theory. This has been done by Hook and Ratazzi, but we, if you want, improved their computations and corrected minor deficiencies. And here is the amplitude that is relevant for the n-to-n scattering. And you see, not surprisingly, the appearance of this ratio omega over 4 pi f to some power, but divided by some factorials of n. And so you can put that in a computer and numerically impose the perturbative unitarity bound and deduce the bound on omega, so the cutoff of the theory. Here there has been an identification actually between the center of mass energy in flat space and the oscillation frequency omega, which is natural given that the resonance occurs inside the horizon. If you want to have an analytical understanding, you can look at the regime of large frequency, in which case you will find the maximum of that for that n max, and confirm indeed that there are logarithmic correction that makes lambda cutoff greater than 4 pi f. Then the recipe is easy. We actually know very well all the endpoint function at first order in B. They all correspond to simple contact diagrams, and they have been computed already 15 years ago with well-understood amplitudes and shape of each endpoint function. Then the real work was actually to construct estimators for these endpoint correlators and compute their signal-to-noise ratio. So let me skip details, but there's a well-known recipe to do that compares, if you want, the theoretical signal and the signal in the sky through estimators that generalize the well-known ones for the three-point function. And we can compute the signal to noise for each endpoint, and also for the optimal estimator that combines all that. And the total signal to noise squared is actually just the sum of each of them. The real work is to compute this now, and here is the result simply. It's been a lot of work, but the result is simple. The number of modes in your, let's say, hypothetical survey crucially plays a role. If you have an infinite number of modes, if you have an infinite precision, the signal to noise is infinite. So it makes sense that this appears, and you can think of this number of modes as roughly 10 to the 9 for, let's say, current and upcoming large-scale structure surveys. You recover this polynomial growth as omega over 4 pi f to some power. So the signal to noise, when omega is greater than 4 pi f, initially grows with n, and then decays because of these factors of n factorial. And actually, the maximum amplitude of the signal to noise is reached for the same n max as for the scattering amplitude. If you look at that in a plot, here is what it gives you. So here, this is the signal to noise for each endpoint function divided by the number of modes. So if you think that 10 to the 9 is the typical number of modes that we have in mind, when this quantity is larger than 10 to the minus 9, it means that we can have, hypothetically, a detection with large-scale structure surveys. For each plot, we look at different values of B, so smaller B corresponding to smaller amplitude of the feature. And you see that for as small values as B of order 10 to the minus 8, we actually can have a detection of this signal. And you can also see that the smaller B, the smaller the signal, makes sense. But that for each value of B, we have different endpoint function that contribute. Of course, the actual data correspond to discrete points, but we can actually have identical, if you want, results that give continuous plots for n. So if you look at this value, you would have the maximum signal for the 5-point function, and actually a much larger signal than for the oscillation in the 2-point function and then 3-point function. So that's really something quite new. I should also stress that here, for each value of B, we look at the best case scenario, kind of, where we chose the frequency to be at the cutoff. Here this goes beyond. Here we have a two-dimensional plot where you have on the horizontal axis the amplitude of the feature, on the vertical axis the frequency in units of 4 pi f. So the plot that I showed you before corresponds to that line, okay, when omega is the cutoff. So the green region is excluded. Everything below that line corresponds to a theory which is under theoretical control, where frequency less than the cutoff. Of course, if you diminish too much the amplitude, you will have a very small signal and no detection. And here is actually the boundary of detectability. So here is where the signal to noise for n modes of order 10 to the 9 is 1, so a detection. So the more you move on the right, the more signal to noise, to the point that here you have an enormous detection. So what is interesting with this is that you have all this parameter space in blue, where you have theoretical control and a signal detectable with actually endpoint function roughly between 3 and 9 dominating the signal. That's what is indicated with these different curves. If you are below that line, you're actually dominated by the 2-point function. Fair enough. But as soon as you're here, this is actually the 3-point function that dominates. Here, the 4-point function, 5-point function, etc. So that's our main results. Let me recap. We have a generic method to compute non-perturbatively the tail of the wave function. Its first analytical results of such kind of non-perturbative phenomena from inside the horizon interactions. We have a rich pheno, asymmetry between peaks and trough, oscillations, super resonance, and a new regime with detectable oscillatory signal in large endpoint correlation functions. Open questions, we can apply that to different type of features, go beyond small amplitude, look at the impact of possible UV completions. Also, it's a natural question to ask how we can probe for these signals in the new regime. Maybe it's not the best way to look at individual endpoint functions. And also, we hopefully would like to have a better understanding of the link between perturbativity and non-causality. Thank you for your attention.